So welcome to the Picture Language Seminar. As you can see, we have a very good list of upcoming speakers. Next week, Renchen Ren, then David Evans, Chenkan Wang, Xun Gao, Yo Singlerland, and Sebastian Palku. And today we're really happy to have Avi Wigderson from the Institute for Advanced Study. Avi is an expert in complexity, in computer science and many things. And he's going to tell us about optimization, complexity, and mathematics, or how can you solve P is not equal to NP using gradient flow. Avi, the floor is yours.
Okay, thank you very much. I hope you all hear me well. Let me share my screen and make sure you also see the lecture well. All right. So thanks, Arthur, for inviting me to do this. I want to talk about this long title, and I promise to explain everything about it. I'm going to describe joint work that I've been doing with many co-authors listed here in the past something like 4 or 5 years. And I basically want to excite you about it, summarize it, and explain it. And there's a lot of material here. I'm not sure how much I'll cover exactly. We'll see. I don't know, it's a large audience, so I'm not sure, you know, if you have a burning question, do ask me. And otherwise, yeah, there's plenty of, as I understood from Arthur, there's plenty of time, half an hour at the end to ask questions as well. Okay, so first thing to just highlight is there's such a diverse audience, and whenever I give a general talk to a mathematical audience and P and NP is mentioned, even though this is not the focus of the talk, but it is definitely related and part of my motivation, not just for this work, but I would say for all my work in the past 40 years. Let me give you I think mathematicians by now, maybe scientists in general, know about this computer science problem and its importance. It you know, made its appearance in the Clay Millennium problems, and I think most mathematicians I meet today know it. But let me just give you a very high-level version of this problem to illustrate why it's important. So I always envied physicists for being able to use, you know, real-life objects to explain what they are doing. So let me try the same. Just imagine that this universe, these stars you are watching, are each a computational problem. And we computer scientists are about solving computational problems. Now, there are two particular galaxies of computational problems that we really care about, and we, I mean everybody. One is the galaxy of all the problems we'd like to solve, whether we are mathematicians, scientists, and so on. And this is a class that we call NP. And within it, there is a class of problems we can solve or understand. These are the problems we can basically get to efficiently. And if you take this point of view, the P versus NP question is about whether these two classes are equal, whether we can solve everything we ever want to solve. And given the computational problems typically capture scientific and mathematical and intellectual problems, like problems we want to solve, maybe, you know, theorems we want to prove, the question of whether these two classes are equal is obviously important. So I'll mention it later, but can keep this in the back of your mind and also independent of the lecture. So back to the lecture, I'm going to talk about starting with two problems, starting with one problem and one algorithm, singularity of symbolic matrices, and the algorithm is alternate minimization. But then this will be take maybe half the lecture. And then we'll start internalizing what we've done and generalize it, and then repeat this process. And we'll see how to arrive eventually at what I think is a pretty good understanding, although far from complete, of how to extend the very familiar convex optimization framework of Euclidean space that everybody is using all the time to the setting of geodesic optimization, where your optimization lives in Riemannian manifolds. And we'll talk about algorithms for that and bounds analysis of such algorithms. This repetition of internalizing, generalizing, and so on, this is what we've been through in the past 5 years. And I'd say that I find this problem to have been like a snowball, starting small, and as it rolls down the mountain, just picks up more snow and grows, and its connections to different areas of computer science, mathematics, physics just sort of astounds me. And I want to just flesh out some of the areas that interact here. And interact, I mean, they both serve as sources of problems, they serve as sources of tools, and there are applications to the techniques we develop. I'll just mention them. Non-commutative algebra, invariant theory, quantum information theory, analysis. This is what we more or less started with. Other people recently developed applications to operator theory and in statistics. And of course, our initial motivation, definitely my initial motivation, was in computational complexity, but it turns out to be very related, in fact, fundamental to optimization. So you'll see some of that, some of these connections. I find it really fascinating that all of this play a role in this work. So as I promised, I'll start from one problem and one algorithm. And I'll explain what they are, both of them, because most people may not be familiar with them. And first, I'll start with the problem. And actually, to explain the problem of singularity of symbolic matrices, I'll start from a toy problem and then extend it to that. So let me tell you about bipartite matching. I think this is a problem many people are familiar with. It's a basic problem in graph theory and in optimization. Your input, your data is a graph on two sides and some edges connected it. You can think of, if you have 3 kids like me, it may represent which type of candies your kids are willing or to have. And the question is, if you have 3 candies, how would you divide them so that everybody is satisfied? Or can you? And in this particular case, there is a solution. There is a matching, right? A perfect bijection between the kids and the candies. So this is one graph when the answer is yes to the bipartite matching question. And this is another case, another graph where the answer is no. So sometimes it's yes, sometimes it's no. And it's a very old problem. It's been studied for a long time. Whenever you have a combinatorial problem, and this is a connection we'll see, optimization problem, often it's useful to represent it algebraically, and there's a very natural algebraic representation. By the way, I should say that this problem is so old that even Jacobi in his work on partial differential equations, ordinary differential equations, already found a polynomial time algorithm for this problem. So long before we invented names like P and NP, he just needed it. So he, like many mathematicians in the past, algorithm design goes back to Euclid and before. So this problem is also well solved. It has an efficient algorithm. Anyway, it's often useful to represent problems algebraically. And in this case, one can think of a matrix represented the graph. You put a 1 if there is an edge between two vertices, and 0 if there isn't. That's called the adjacency matrix of the graph. And algebraically, asking whether the perfect matching or not is asking whether the permanent of this matrix is positive. The permanent is just like the determinant without the sign. You have the formula there. I wonder if, do you see my mouse?
Yes.
Yes? Okay, good. So here's the formula in orange for the permanent. It just sums over all diagonals of the matrix and multiplies the entries there. So obviously there is a perfect matching is a diagonal of 1s in this matrix. Okay, so this is an algebraic representation of the problem, but permanent, and we'll see this later, or maybe many of you know, is a nasty polynomial. It's hard to compute. Here we just want to know whether it's positive, but computing it is difficult. So Edmonds suggested a very different algebraic representation of this problem, which is the following. He suggested that we replace every 1 in the matrix by an independent variable. Okay, in position ij, if you had a 1, you put a variable xij. So now the matrix becomes a symbolic matrix, and I'll call it ag of x. And you can ask the same question about perfect matching in the following way, or observe that the graph has a perfect matching if the determinant of the symbolic matrix, which is now a polynomial, is not identically 0. It's obvious because monomials cannot cancel each other as all the variables in the entries are distinct. So this problem, because it's equivalent to the previous ones, has a polynomial time algorithm. So that's an observation. And it's actually an important one. And then he made a leap. He said, why don't we extend this problem? So that problem we could solve efficiently, but suppose the entries of our symbolic matrix is not just single variables, distinct variables, but actually arbitrary linear forms in some set of variables, x. Okay, so each Lij is some linear form. So one way to represent the matrix is just a linear combination of constant matrices over our variables. So AIs, I mean, this makes sense over any field. And you take this formal linear combination of some constant matrices and you get a symbolic matrix. So now you can ask, it's the same question, only generalized to this more general setting, is I give you these constant matrices, A1 through AM, and I ask whether the symbolic matrix is defined has a 0 determinant. That's a singularity question. Whether this matrix is singular or whether its determinant is identically 0 as a polynomial. Now it gets interesting. What do we know about this problem, and why should we care about this problem? So Edmonds asks a question that we still cannot answer to this date, whether it has a polynomial time algorithm. Lovaas observed a decade later that it's very easy to give a probabilistic polynomial time algorithm. I mean, basically just choose random values to the variables and evaluate the numeric determinant. And of course, if the determinant was identically 0, you'll always get 0. If it was not identically 0, the probability you will hit, you'll fall in the variety is negligible. So that's good. That's progress. It's efficient algorithm, but probabilistic. Why is this problem interesting? There are several reasons. Valiant discovered, independent, unrelated, it's the same year, but this type of problem captures essentially all algebraic identities we care about. If you have your favorite ones, it can be expressed in this form, whether the determinant of a matrix is identically 0. So it's some kind of universality result for this problem. This problem appears naturally in lots of areas of mathematics, modular isomorphism, graph rigidity, and many others. And perhaps the most important and sort of shocking understanding of the importance of this problem comes from a result of Cabanet and Impagliazzo. So let me state it, and let's reflect about it. So here's the result. Suppose this problem had a polynomial time algorithm, deterministic polynomial time algorithm. Let me highlight. Then you can infer something like P is different than NP. You can, solve the holy grail of computer science and beyond. I put it in parentheses because it's something similar, and I'm not going to explain the difference, but it will, sort of teach us something we are far, far, far from understanding about this problem. That's one reason it's important. A reason it's peculiar is not it's a statement for those who've never seen it. Should be really interesting. The consequence is that P is different than NP, namely that some problems are difficult. But the assumption is an algorithm, an efficient algorithm for a problem. So it's sort of really bizarre that if you have an algorithm for a problem, a very specific problem, I just described it to you, then you can prove a lower bound on tons of problems, that many problems are hard. Anyway, that's a major motivation to study this problem, which we will do. As I said, we are not going to solve it. It's a problem about proving lower bounds, why I care about it. It's also a problem about de-randomization. We already said that we have a probabilistic algorithm for this problem. Can we do it without randomness? So these are my main motivations. Anyway, let's look at this problem, the singularity problem. That's our problem, but actually now I'll show you the dual life of this problem. So here's the problem again. We are given M matrices in this invariant matrix where they define a symbolic matrix. And we want to know whether this symbolic matrix is singular. Until now, I didn't say anything. I'm sure you all assume that the variables commute. When you talk about commutative variables, the singularity of such a symbolic matrix is just whether it's singular in the field of rational functions in these variables. And as I said, we don't know much about this problem. We know that it has a probabilistic polynomial time algorithm, and we really, really, really want to find out if it has a polynomial time algorithm. But I also said that we don't know how to solve this problem. So like good mathematicians, we are going to change it. And we look at the same question, singularity of symbolic matrices, when variables do not commute. So the first question, what does it mean, singularity? Where do we want to invert this matrix? And there is a natural answer. It's in the field, which is a completion of non-commutative polynomials. It's called the free skew field. I'm not going to define it. It's a really complex beast. And actually, it's interesting because of that. But I'm not going to define it. So in some sense, I'm not going to define right now the problem we want to solve. But I'll give more elementary definitions later of this problem. I just want to talk about this problem. This problem was studied also in mathematics, non-commutative algebra, in particular its complexity. And unlike the commuting case, it's not even obvious that this problem is decidable. In fact, it took some deep work of Kohn in the 70s to prove that this problem has an algorithm, a finite algorithm. Then people started working on improving it, and Kohn and Rethenauer found an exponential time algorithm, and that was more or less it. And the main work I want to describe in the next 15 minutes is our algorithm giving a polynomial time solution to this problem, to the non-commutative case. Okay, so non-singularity in the non-commutative case is in P. This is for the rationals or the reals or the complex. Soon after, Ivanioskar and Subramaniam gave another algorithm, very different, for essentially all fields. I'll talk about our algorithm and will not discuss theirs. Okay, so I want to describe now the algorithm. The algorithm is of the form called alternate minimization. We'll discuss it more, but I want to exemplify it on the problem with, first of all, the toy problem of matching, and then for this problem. Recall the perfect matching problem. That's one presentation. In fact, we saw several representations of it. And in order to apply alternate minimization for it, I want to give you an equivalent definition of perfect matching problem that looks very different, but is useful to applying this algorithm. And this is a problem of matrix scaling. What's the matrix scaling problem? The input will be a non-negative matrix. It can already be a doubly stochastic matrix. I remind you that a doubly stochastic matrix is one whose row sums are 1 and whose column sums are 1. Okay, but maybe the matrix is not doubly stochastic and we want to make it doubly stochastic. Okay, good. So what are the rules for I allow to make the matrix doubly stochastic? I allow scaling. What we are allowed is to multiply the rows and the columns by scalars, non-negative scalars. So in other words, what we are allowed is to multiply them from the left and the right by diagonal matrices. And we want that after this process, the matrix will be scaled, namely will be doubly stochastic. And actually, let me insist now that all I care about is that we can approach double stochasticity. So the question I really want to ask is whether we can, for any epsilon you give me, there will be matrices, scalars that will make all the row sums and all the column sums 1 within epsilon. Okay, so that's the doubly stochastic scaling problem. And as I said, it is equivalent to the perfect matching problem. So that's why we'll study it instead. This connection is not complicated, but I'm not going to go into it. People looked at this problem for many different reasons. It sort of turns out to be important, but let me not get into this. Anyway, it's equivalent to perfect matching. How do we solve it? Okay, so I give you this non-negative matrix. Let's say it's a adjacency matrix of this graph below. And I ask you whether you can make it doubly stochastic. This question of scaling is sort of interesting. I mean, you have, let me go back here. You have 2n conditions, right? Row sums are 1, column sums are 1. Actually, there are maybe 2n minus 1. And what the freedom you have is choosing 2n scalars to make it so. And so it looks like a fair game, but it's not clear how to do it because one interferes with the other. So how can we check if there are such scaling constants or diagonal matrices that will do that? Well, while doing all of them at once seems difficult, definitely, taking care of the rows is easy. So let's do separately the rows and the columns. Let's be really, I don't know, this synchronous algorithm, and actually many others came up with it independently. It's a very greedy approach. We'll try to make the row sums 1, and then we'll take care of the columns and repeat. So this is what alternate minimization is. Okay, let's do it in this example. Making the row sums 1 is very easy, right? You divide the first row by a third. But now the first column is bad, so let's fix this. After doing that, we have the row sums are not good, so let's try to do this. And maybe you see where it's going to, but I'll tell you. Eventually, you run into this cycle. It's not converging, this process. There's no convergence, but remember, I told you that this is the adjacency matrix of this graph, which has no perfect matching. So maybe it's good that this process doesn't converge and this graph does not have a perfect matching. So let's do another example, but before that, let me just write down the algorithm more formally. I mean, basically what we are doing, we are given a matrix, and we keep alternating either dividing by the row sums, right? Dividing every row by its sum, or dividing every column by its sum. very simple algorithm, and we repeat some small number of times. That's the alternate minimization heuristic. It's sort of, the problem is partitioned, and you solve different parts independently and just repeat. So let's apply it to this matrix, which is the adjacency matrix of this graph, which does have a perfect matching. And let's see how this goes. So let's scale the rows, right? Then we can scale the columns, scale the rows. You may see what's going on. I mean, the off-diagonal entries get smaller, and the diagonal entries get larger, and that's the limit. That's what it will converge to. So it converges in a graph which has a perfect matching. So at least these two examples, it's a good algorithm. Let me say it again, what this algorithm does in general, again. So it repeats these two operations, does so n cubed times. Let's say if the entries are 0, 1. And then it tests whether these row sums and column sums are close to being all 1, up to 1 over n in any norm you want. And declares that, you know, if they are close, then the permanence is positive, there is a perfect matching, and otherwise that it's 0, there is no perfect matching. That's what the algorithm declares. The main question, why does this algorithm work? Is it good? Why does it, you know, can we stop after so few steps? So I want to describe to you in high level an analysis for this algorithm that we came up with Lina Samolnitsky about 20 years ago for entirely different reasons. This algorithm is of the family of basically dynamical systems, right? I mean, you keep evolving. Yeah.
Boaz has a question.
Okay. Yeah.
So I guess I can unmute. So yeah, I was just wondering, in this case, the algorithm converged to the perfect matching itself. Is it in general converging to a convex combination of perfect matchings?
Yeah, it's actually a very interesting question. You will get a doubly stochastic matrix. The support of that matrix will have the property that it always contains edges that appear in some perfect matching. So the answer is yes. It doesn't have to have all of them. But the meaning of the numbers in the matrix is very interesting. Anyway, and it does not, as described, does not find the perfect matching, although you can turn the algorithm to find a perfect matching. Okay, let me explain the analysis of the algorithm. So it's a dynamical system, as I said. I mean, you are just creating more and more matrices in this evolution. And the natural way to analyze dynamical systems is by picking the appropriate progress measure. And the one we picked in that old work was the permanent itself. We want to see how the permanent of this sequence of matrices evolves. And it's the 3 steps in every such proof in dynamical systems are always the same. You want to show that throughout the sequence, this progress measure is bounded. Here it's easy to see that from the first one, it's bounded by 1. You want to show that it grows, and it grows at least whenever it has room to grow by a factor 1 plus 1 over n. Both of these steps are really easy. The second one follows easily from the arithmetic mean, geometric mean inequality. And the last thing you want to show, if you want convergence, is to say that you don't start too low. It turns out that if the permanent of the matrix is positive, then, and stochastic, let's say, because row sums are 1, then the permanent is at least 1 over exponential. So you can see easily that if you iterate this, let's say, cubic number of times, you will get close to 1, very close to 1, and then the algorithm will answer the correct answer. So the analysis here is easy. It's really, really easy. Okay, so we have an algorithm for perfect matching. It's it was known, different algorithms was known. It's very different than the algorithms we learn. But anyway, we have an algorithm. But like I said, this was a prelude to describing an algorithm for the symbolic matrix singularity problem. So for this, we are now going to look at the singularity problem and want it to look like a scaling problem. And this was done by Gurwitz. So I'll explain Gurwitz's idea and then the algorithm and its analysis, which will be very similar. The algorithm and the analysis will be very similar, and we'll get to see what was difficult here that was all easy before. Okay, so I know there are some people in quantum physics in the audience. Don't want to insult everybody. I'm going to give a caricature first.
Avi, there are a couple of other questions, one from Emmanuel and one from Peter Shore.
Yeah.
Emmanuel.
I'm listening.
Oh, yeah, sorry, I couldn't. Yeah, I was just wondering if you could give some intuition on why the permanent grows, your second claim in the analysis.
Yeah, it's a one line. I mean, basically, when you are dividing by row sums, if you use a arithmetic geometric inequality, you see that it at least doesn't shrink. That's straightforward. Why does it grow? Because the arithmetic mean geometric mean inequality is tight only where everything is equal. And if you are far from being, you know, say row stochastic, then it will grow. It's really simple. I have a slide for it. I can show it at the end if you want. More questions?
No, Peter said to go on.
Yeah. So let me describe first, you know, very caricaturistic view of how you quantize the problem. And this will be the relation between matrix scaling and the operator scaling that I'll define. In matrix scaling, we have a matrix that we wanted to scale, the row sums and column sums, to be one by left and right multiplication by diagonal matrices. And the operator will be just a tensor. You know, we go in quantum, we usually go one dimension higher. So we'll have a tensor tuple of matrices, and we'll scale them by just non-singular matrices. So basically, we'll move from matrices to operators, from the L1 to the L2 norm. The notion of double stochasticity will be natural. It will be whether this sum AI transpose is the identity. That will be like the row stochasticity, and column is the same with the transpose. And as I said, scaling will be by invertible matrices. You know, vectors go to matrices, or diagonal matrices go to non-singular matrices. Okay, so what was Gurwitz's insight? He wanted to solve the singularity problem, the Edmonds problem. That was his interest. So on the left, you see the problem. You remember that given a tuple of matrices, it defines a symbolic matrix. We asked whether it's singular. That was his interest. And what I said we'll solve is non-commutative singularity. But anyway, it's a very particular algebraic looking problem. He translated it to a problem in quantum information theory about quantum operators. So a tuple of matrices can be viewed as symbolic matrix, but can be viewed also as a quantum operator. So how do you do that? Well, M matrices can define an operator on matrices, right? Any matrix P transformed to some AI P, AI dagger. Okay, this turns out to be the most general quantum operation in quantum mechanics, or a noise operator sometimes. It is positive in the sense that obviously if you input a PSD matrix, you also output a PSD matrix. Okay, we said we had a notion of double stochasticity. In fact, we have a notion of scaling. So we can try to scale such operators. And what Gurwitz asked itself is, or in fact had the insight, that this is connected, this question of whether you can or cannot scale it is connected to the singularity problem. What it proved, so this is the operator scaling problem, can you scale it? The question, or what he showed is that if you cannot scale it, it means that it's commutatively singular. But that's just a one-directional connection, and maybe that's the reason we cannot solve this problem. And a starting point for us was observing, and this follows work in non-commutative algebra, that it is equivalent, the scaling problem is equivalent to the question of whether L, symbolic matrix, is non-commutatively singular. So now we can just try to see if we can scale L. And in fact, Gurvitz started and went a long way towards doing it. He just suggested to generalize the scaling algorithm for matching and generalize the LSW analysis. And let me show you what he suggested. You don't have to read it. It's precisely the same. I give you an operator. You either pre-multiply or post-multiply by an invertible matrix to make it either row or column stochastic in the same sense. You run it for some number of times and see if it's close. And then you declare accordingly whether it's singular or non-singular. It's a very natural generalization. If you want to analyze, you need, whatever is the analog of permanent that we had before. So he invented the progress measure to analyze. This is called the capacity. Again, you don't have to read it. It's very natural, naturally defined. What's important about it is that it proved it, matches perfectly. It's positive when the operator is a symbolic matrix is non-singular and otherwise zero. Or it follows from his work. He was not looking at non-commutative singularity, but follows from his work. So it is a problem we want to solve. And then he said, well, let's try to run the LSW analysis with this progress measure. And the first step is easy. The second step is easy. In fact, they are the same. They are essentially the same proofs. And the last thing you need in order to prove that it converges quickly is to prove a lower bound on capacity, as long as the capacity is positive. So an exponential lower bound suffices, again, because the algorithm progresses, capacity grows geometrically like before. But this it couldn't do, and it was left like that. And the main result I want to explain or talk about, or mainly generalize, is that this is true. You get this exponential lower bound. But it turns out that it's not easy. In fact, you need tools beyond combinatorial, obviously algebraic, maybe linear algebraic tools. What you need, this implies efficiency. You need to understand, and I'll talk about it soon more, that there is invariant theory involved. There is some group action. This algorithm, is based on a group action that the measure capacity or permanent beforehand were invariants, actually more precisely semi-invariants of this action. And the analysis of this particular lower bound, I will not show it, but uses some really deep results in the degrees of invariant polynomials. So I'll explain all these terms in 2 slides. Anyway, you need tools to prove this. I just want to talk for a second about the consequences of this efficiency of this algorithm. So it solves the operator scaling problem and therefore non-commutative singularity. But in fact, I alluded to this in the beginning of the talk. There are connections to many areas of math and also physics. And it comes from what Gurvitz did, turns out to be much more general. A tuple of matrices, as I said, is just, can be viewed in many ways. It can be viewed as a tensor or a set of linear maps, or can be described as input to a determinant problem and more. And it turns out that I just listed for you 6 different problems in 6 different areas Let me not go through them, but there are really 6 different areas. In some of these areas, they are just natural problems. In some of these areas, there are fundamental problems, like it's the word problem for non-commutative algebra, captures the word problem for non-commutative algebras. And all of them, so the first 5 are equivalent, and the 6th is just a special case. So equivalent, I mean equivalent. The answer is yes to one, if and only if the answer is yes to the other for any given tuple of matrices. Okay. And so when we solve this problem, when we gave the sufficient algorithm, in fact, we solved all of them in all these areas. They all have efficient polynomial time algorithm. Okay, so now I want to talk about the tools that go into proving this and how these tools actually led us to generalize the problem, the algorithm, and our understanding of this, what we can do. So I have 20 minutes for that. Okay, so invariant theory is the main source. And what is invariant theory? It's a field that studies symmetries through, formally group actions, and you look at orbits and invariants of this action. So let me give you a couple of examples you are familiar with. You can permute the names of the vertices of a graph using the symmetric group, right? So that's an action. One goes to the other using this action. You can, if you play pool, what the group acting here obviously is time. So the real line, once you hit the white ball, the evolution of states of the system, you can pick it up at every point of time. And you may know this or played with this when you were kids. You can take a shape, cut it with scissors, and transform one shape to the other by moving the pieces around, let's say without overlaps. And in each case, there is some dynamics. You have some group. You can move one shape to another, one state to another. Everything you can move to with these groups is the orbit of this group action. But despite of this sort of dynamics or many states you can reach, there are things that never change, and these are invariants. That's why invariant theory is called invariant theory. You are looking for these functionals which do not change with the action, right? So in the last example, it's well known that area doesn't change. Well, of course, area doesn't change. What is much more interesting is that area is the only invariant. It's the only thing that doesn't change, only functional. In the physics case of the pool table, we learned in high school maybe or college that energy and momentum are invariants. And in fact, they are the only invariants if this is elastic collision, say. In the case of graph isomorphism, here we have no idea what the invariants are. So some of these problems are very difficult. For our talk, the type of group actions we will mention are actions of linear groups, let's say of matrices, and which act on vector spaces. I'm not mentioning various, asterisks, rational actions. These are, it's not all linear groups and so on. I will not get into this. Important here is that this theory has 2 sides which are interplaying beautifully here. One is the algebraic side. In particular, all these actions have polynomial invariants, and a geometric side or analytic side that we will get to later, in particular, a rich duality theory. So I want to say, computer scientist that I am, I started giving survey lectures in invariant theory because, whenever I want to explain it in more details. I'll just give you a 1-slide summary of the things that are most relevant to this talk. So we look at groups, linear groups that act on vector spaces. So they act on polynomials. If the vector space is dimension k, it acts on polynomials in k variables. And here are some examples. Okay, so the orbit is every vector you can get to using this group action from a given vector v. And since we are in the continuous setting, the orbit closure will also be interesting. You had all the limit points. The invariant ring is the ring of polynomials that does not change under this action. So all polynomials, so if you apply it to anything in the orbit of V, you get the same value as when you apply it to V. And here are two examples that you know. That's if G is a symmetric group acting on the just permuting coordinates, then the invariant ring, the polynomials which do not change in this action are simply the elementary, all the symmetric polynomials. And here we know they are generated very concisely by the elementary symmetric polynomials. So there are infinitely many, but we have n of them that capture all. Here's another example that you are familiar with. The group is pre and post multiplying by non-singular matrices, so a basis change of the determinant one, say, acting on matrices. So you change the basis on the left and on the right. What are the invariant polynomials here? Well, it's very easy to see that only the determinant and its powers. Determinant remains and nothing, no other polynomial of the matrix entries is invariant. So they are very simple examples. And it's a very fundamental problem for us, a fundamental result for us and for mathematics, that invariant rings in general, in this general setting, are finitely generated. And in particular, the quantitative question of degree bounds, once you know it's finitely generated, then, well, in what degree? Like in the previous two examples, we saw that degree n is enough. It turns out that for the analysis of the algorithm I showed you, it's absolutely fundamental that we know bounds on the degrees, exponential bounds, on the degrees of the invariant polynomials generating the invariant ring. So that's one important concept. And the last one I wanted to say, because this will soon meet it again, is the null cone. The null cone of a problem, of an action, is all polynomials which vanish, all vectors in the vector space which vanish under all invariant polynomials. That's a null cone of a group action. It's an algebraic variety. And it turns out to have also a very interesting analytic definition, which we will also see. It's a result by Hilbert and Mumford. Vector is in the null cone if and only if it can be driven, its L2 norm can be driven to 0 by elements of the group. So that's an analytic definition. And this is important because, first of all, let me tell you, all the problems you've seen so far are all null cone problems. These are the problems solved by these algorithms, and we'll see more. So that's one reason we should be interested in the null cone. And of course, this theorem here is this connection I mentioned already between the analytic and algebraic views is very important for this and, of course, more generally. In the two examples I showed you, the null cones are really simple. Here it's just 0. It's a finite group. It's always like this. And in the case of the second example, the action on matrices, the null cone is simply all singular matrices. So null cones are very natural objects. The membership in a null cone, which is a problem we will ask, as I said, all problems before and later will be almost all will be like that. It turns out to be dual to scaling problems. I described the problems before as scaling problems. It turns out to be essentially the same question, and many problems we know are captured by this. So we really want to understand null cone problems and scaling problems, which are the same thing. Okay, so now that we have this information and we've seen the algorithm we had two algorithms we developed, let's try to unify, generalize them in more or less the obvious way, the natural way. So here are the two problems and the two algorithms, reminding you again. The algorithm were alternate minimizations. We applied really group operations on the left and on the right. So that's a very fundamental insight. Now we didn't have to describe it before. Scaling by constant or multiplying by matrices has an obvious meaning to any college students, but now we really want to think about it as an action of a group on the input. And we had our analysis, which we will also try to generalize, choosing this potential function. Okay, so let me talk about each of them. And sorry, and the problems themselves were scaling problems, and I said they are equivalent to null-con problems. So how do you generalize it? Well, let's first talk about the algorithm. So the algorithm is alternate minimization. Let me just present it in the general form. There are many, many examples. This is one of the most favorite heuristics in optimization, statistics, in machine learning. You're trying to solve a complicated problem in many parts, let's say k parts, and it's a complex problem. Maybe it's an optimization problem, maybe it's a sampling problem. But it turns out that each individual part, if you fix all but one parameter, then solving this, optimizing just this single parameter is easy. And this was the case in the previous examples. In general, this is far from being understood. And what we can do now is at least understand it in the setting we have, which is a group theoretic setting. So a much more general problem that we can look at is just, have a action on tensor, action of products of groups, diagonal, not singular, whatever. Each coordinate acts on fibers in a particular dimension, and I'll tell you soon why it's interesting. But definitely the natural, generalization. And we can ask, given a vector, namely a tensor like this, can we scale it? Scaling has the obvious general meaning. You can want row sums, column sums, and in all directions to be one, or the appropriate generation of identity matrices, as in operator scaling. Anyway, that's a natural problem. And it turns out that the same algorithm, you just iterate scaling one particular coordinate at a time, leads to a polynomial time algorithm in the obvious parameters. And I remind you that this problem is not convex. I mean, in fact, the domain is just a bunch of linear groups of complex numbers. So it's not clear why such an algorithm exists, and we'll talk about this soon. And just to tell you why we are looking at these problems, this type of problems, as I mentioned, well, there are scaling problems and equivalently null-con problems, and in different dimensions, they capture problems in different areas. We talked about the two-dimensional case, which is basically matrix and operator scaling. In 3 dimensions, it captures, I'm not going to explain this, the asymptotic Kronecker coefficient question from representation theory. And in any dimension, it captures entanglement with distillation. Well, let me say what this one is. I mean, you are given a k-partite state divided across k-partite quantum state divided across k players, and they each can apply a local operation to their state. And what they want to achieve is that to create maximal entanglement between each player and the remaining ones. So it turns out this is a problem that naturally is captured by this formulation. There's a slice rank problem in tensors, which is a combinatorial problem, and many others are captured by this, and I mentioned others already. And repeating, we have this algorithm for them. I want to stress that even though this algorithm is polynomial in 1 over epsilon, this is not always enough. Sometimes the epsilon we need is smaller than polynomial. So it's not always giving polynomial time algorithms, it's giving it only for some of them. And the important thing is that the analysis is exactly the same as what we've seen. It's the same 3-step analysis. The potential function turns out there is a universal one. and has to do with the Hilbert-Mumford theorem. The potential function will be just, we don't need permanent or capacity. We just can look at the L2 norm of the vector. And as before, the 3 steps work magically, you know. The first 2 are really easy and follow essentially the same format. And for the third one, namely proving that if a vector is not in the null cone, then there's some lower bound on the L2 norm. This turns out to require, in this more general setting, more invariant theory, more representation theory that I'm not going to get into. So let's, you know, now that we see it, we have a general algorithm for a general setting that's often efficient. There's something really strange going on. I stress that these are non-convex problems, and we see a very simple, greedy algorithm which converges and often fast. What's going on? Another is that I mentioned this connection between scaling and non-convex problem. I want to tell you something about it. Yeah, I have maybe 5 minutes, so we'll see how it goes. And another question is what, you know, this is still a restricted framework. Can we say something about the action of general groups or general linear spaces? And I hope to say something about this, but let me try see what I can get in these last 5 minutes. This is the next round of unification or generalization, if you will. And for this, I need to talk about this non-commutative duality, about geodesic convexity, and the moment map. Okay, so here again are the 2 problems and algorithms we started with. And we had this goal, which was scaling, and the analysis, which was chosen to minimize the potential function. I told you, actually, the L2 norm is always good for this setting. So what I want to do now is switch the goal and analysis. Suppose that our goal was really to minimize the potential function, minimize L2. So let's start with this and see what we get to. So assume now we have an arbitrary linear group acting on a vector space, doesn't have to be of this product form. And the goal, the new goal, as I said, I give you a vector, and we want to minimize the length of the vector in its orbit. So as in the picture below, we want to find V star of the smallest norm in the orbit. In particular, I remind you that, okay, so it's an optimization problem, and as I said, it's non-convex. I remind you that testing whether this norm is 0, whether you can approach 0, is an outcome problem. So it's very natural for us to study this. And in fact, for invariant theories, as they did. And when you think about the problem, at least, you know, computer scientists, you don't know how to solve it, you at least ask whether you can certify it. And we already know that we can certify, you know, the non-membership in the null cone. We can certify that the minimum is positive. How do we do that? Well, by the algebraic connection, if we can present an invariant problem which does not vanish on the vector, then it's not a 0, you know, then it's positive. So we know how to certify the positivity of this minimum. How do we certify that it's 0? Is there an easy way to explain when it is 0, even before computing it? And that's the content of the important Computational duality theorem. It says that the value of this optimization problem is positive if and only if the value of another function, the moment map, on the minimum point, on this non-zero point, which is on the orbit, is 0. What is this moment map? I'm not going to define it, but it's really a natural non-commutative analog of the gradient. Well, it's basically, if you do an infinitesimal move to your vector, an infinitesimal in the group sense, you act on it by a group element close to the identity. How much does the norm, the L2 norm changes? That's basically it. So you look at this and you see that, if we want to certify zeroness of the optimization problem, we just have to prove that the moment map is positive. And this is really a central theorem. It has many implications, and I'll just mention a couple. They're important for us. If you try to understand what minimizing the moment map is, you just write it down. And it turns out, definitely in the two examples, matrix scaling, operator scaling, it comes out to be just just these problems. So it's dual to minimizing the L2 norm. That's one message. Another thing is maybe not be obvious from the presentation of it, but this is a vast generalization of LP duality. So knowing how important LP duality, linear programming duality is, you can imagine how important this is. But the main thing I want to stress is that how can this theorem be true? You look at it, and obviously there is a local condition, right? The minimality of the zero value of the moment map that implies a global condition, that there is no other vector in the orbit that has a smaller N2 norm. There must be some convexity here, and there is. It's called geodesic convexity. And that's, so there is, despite my repeating myself saying these are not convex problems, they are not convex only if your point of view is that straight line is a short distance between 2 points. In the setting of these non-commutative group actions, you have geodesics which don't look like straight lines. And if you look at a geodesic as the shortest distance, they become convex. That's the message here. And so we can imagine, and we do, in the last slide I'll show you, extend Euclidean convexity and all the algorithms that come with it to Riemannian manifolds. So this explains, at least intuitively, why, I mean, the existence of this convexity, why these algorithms, these naive, greedy algorithms converge. And it suggests this extension of the body of work in Euclidean convexity optimization to the geodesic setting. Now, this is not, geodesic convexity and algorithms for it are not new. This was, of course, studied by Gauss and Riemann and many others. And there are even books on algorithms in the geodesic setting. What we offer here is a new quantitative complexity analysis, the theorems I showed you in the last slide. We say it in general in this geodesic setting for these kind of problems. So imagine this really is the last slide besides the open problems. Imagine now any group action on any vector space, and we want to approximate the L2 norm in the orbit or the moment map in the orbit. When you talk about approximation, these are different problems, even though the limit is the same. And we have just the analogs of what is the sort of holy grail in the case of Euclidean optimization, convex optimization, first and second order methods. So let me just flash them. And first order is what you do if you have only derivatives. Second order is when you have access also to the Hessian of the function. And yeah, we get the same type of results, polynomial 1 over epsilon convergence or polylog 1 over epsilon convergence in these cases. And the main question in all of them, even the Euclidean case, what do you mean by a constant factor there about the number of iterations? And it always, in both cases, depends on the smoothness of the action. What happens in the geodesic setting is understanding it depends on invariant and representation theory, and I'm not going to get into this. But these are very natural parameters and easily explained. Okay, good. So this is a summary. That's what our understanding is today. We have these very general algorithms, and let me just jump to the conclusions, if I can get to this. Okay, so just there are general themes you've seen, and I want to stress them. The interaction between computational questions and algorithms with mathematics and physics is extremely rich, and it goes richer there. There was a lot of interplay between analysis and algebra here. The algorithms, even though they solve algebraic problems, they are sort of analytic, dynamical systems. And even though they are continuous algorithms, we use algebra to analyze them. And of course, that symmetry, group actions is prevalent, and many problems we know and love and not presented in this way are like that. What next to do? As I mentioned, some of the algorithms are exponential, and we'd love to improve them. We'd love to see combinatorial optimization applications to these algorithms. I mentioned perfect matching and maybe mate-weight intersection, stuff like that. These are solved problems. I'd love to solve a non-solved problem in combinatorial optimization using these tools. All the problems I mentioned are null-con problems. Perhaps there is a polynomial time algorithm for all of them. And back finally to the PNP connection I mentioned at the beginning, the algorithms are for null-con problems. Non-commutative singularity was a problem like this. Is commutative singularity a null-con problem? Maybe if it were, maybe such gradient descent algorithm would solve it and thereby prove, things like P different than NP. And I just want to mention a recent result, some kind of, you can think of it as a lower bound or limitation. It turns out that this algebraic variety, the commutative version, is not a null-con problem of any group. So at least this explains something about its hardness. Okay, thank you. Every talk I finish with this ad. So thank you very much.
Thank you. Thank you, Avi, for such a wonderful talk. It united so many different fields: analysis, algebra, geometry, gradient flow, complexity. And we look forward not only to the beautiful results you talked about, but to many ones in the future. So there must be many questions. We're a little late, so we'll have to have only a few questions, but just speak up if you want to have a question for Avi.
Well, that's usually a sign either that everything was completely clear or that nothing was clear. So.
Chenwei, you've thought about these connections between different fields. Do you have any comment?
So maybe, here's, it's not a precise question, but I'm wondering, have you seen this other line of work coming from Princeton, Elad Chazan and Nadav Cohen, on showing that the geometry that gradient descent induces when it does a non-convex objective, like minimizing a deep network, becomes like traveling on some Riemannian manifold. Are there connections between the two things?
I think that this problem and many problems in machine learning are non-convex in more complex ways than here. I would say that, yeah, I saw this. I cannot answer you directly about their work. It seems to me that, well, this would be a really nice goal to strive at. Whenever you can show that your algorithm converges is because you are traveling on some Riemannian manifold and therefore have really have convexity somewhere, then you explained everything. You have a rigorous analysis of convergence, and this will be the positive sign. I just fear that the landscape of the minima of optimization problems that arise in machine learning is not like that. It's much uglier. And there are many local minima that are not global minimum. Right here, there's only one global minimum, which is, there's one local minimum, which is a global minimum. Yeah, so, but on the other hand, maybe techniques, can be adopted to some of the things that they do. And maybe this work, which now that you mention it, I'll look at it again, offer such connections.
I have a question. So you mentioned, this is Robert Lim, you mentioned about the geodesic convexity, how it generalizes the some usual notions of convexity. So when we have convexity, we have a Legendre transform. Do you know whether there's some analogous transform in the geodesic convexity case?
Yeah, I'm going to this, but I'm not sure that it's needed. I don't know. I didn't think of this, but it's a good thing for me to look at it and see. The reason that this theorem generalizes LP duality is actually very simple to see. It's if you look at the action of commutative groups like the torus, which is the action in the case of matrix scaling, then you get, that this theorem translates directly to LP duality. So it's a very simple thing to see. But about the Legendre transform and its connection, I don't know.
Thank you.
Are there other comments or questions? Well, I see there are many people from an audience that's somewhat orthogonal to our usual one. Perhaps there's some comments in a different direction.
There's a lot to digest from this talk, actually. So,
thank you, Rod.
Yeah. The slides will be available as I promised. Arthur, and the papers are all on my website. And for those of you who really have time on your hands, I've given 3-hour lectures on this and 6-hour lectures, and some of them are on my website as well. So.
Well, Avi, I'd like to thank you again. It was such a beautiful experience, and invite you to come back and interact with our set of people, because it's very interesting to have insights from one field of mathematics to another, and the connection with physics comes very naturally. So Avi, thank you so much for this talk, and thank you everyone, and we look forward to coming back next week and hearing the talk of Brainchain 1. Bye-bye. Bye-bye.
Yeah, thank you very much.
Bye-bye.
Bye.